Okay, hello and welcome. It's SFU Math152, Calculus 2. We are on section 11.3, the integral test and estimate of sums. So what we're going to do in this lecture is we're going to see that we can use the integral that sort of is analogous or matches with the particular sum, the infinite sum that we're looking at, and we can use that to get an estimate of the sum. We can use it perhaps to bound the sum, and we could perhaps even use it to see if the series converges. So let's take an example to start this. Here's a graph of y equals 1 over x squared. And we could, and we have in fact, evaluated this improper integral here. So you could go ahead and do that right now if you liked. Maybe I'll just do that here on the side, because maybe stop the video. Remind yourself how to do an improper integral. So I'll just put this over here on the side. That's going to be the limit as t goes to infinity of this integral here. It's an improper integral of type 1. And then it's a simple integral to do. That will be the integral of 1 over x squared is minus 1 over x. That's evaluated at 1 and t. And then that's going to be the limit as t goes to infinity of minus 1 over t plus 1 over 1. And when t gets very large, this term goes to 0, so that we have 1. So the integral, the area under this curve from 1 to infinity is 1. That's just totally remarkable. Okay, next thing what we're going to do is take a look at how that relates to this sum. And we have a sum here, which of course at the points, at the integers, this thing here at the integers matches this thing here. They're the same. I mean, when x is 1, it's 1 over 1 squared, and when n is 1, it's 1 over 1 squared. When x is 2, it's 1 over 4, and when n is 2, it's 1 over 4. This guy here is not defined for values except the integers. This guy here is defined for all real numbers. Okay, I'm now going to draw a picture of what this sum looks like on the same graph. So the first, okay, so what are the numbers here? Here it looks like this: 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus ... It's the sum of the reciprocals of the squares. So these things are all squares, and I could think of them in this way. I could draw a square right here like that, and what would be the area of that square? It would be 1 over 1 squared. I mean, the height is 1 over 1 squared, that's the height, and then the width is 1. So I multiply 1 times 1 over 1 squared, I get this area right here. And then if I look at the next number there, 1 over 2 squared, well, I have a rectangle here also of width 1. Well, I make my rectangle here like that, and the height of this rectangle is 1 over 2 squared, so the area is the width times the height, so 1 times 1 over 2 squared, so the area right here is 1 over 2 squared. And then the area right here is 1 over 3 squared. So the first thing you could see is that, I guess with the exception of this rectangle here, which is here, what I'm trying to say here. We know this area is starting from 1, so that we started this area from here, the improper integral. So we could see that the improper integral, the area under the blue line, is more than the area under all of these squares. We just have to, and then we've got 1 square here of area 1. I mean, this isn't going to affect the finiteness of the situation. So what I'm saying here is that 1 over 1 squared plus the integral from 1 to infinity of dx over x squared is equal to 2, because we evaluate that to be 1. And we know that is greater than the sum of n equals 1 to infinity over 1 over n squared. Okay, so we have now actually got an upper bound on this thing. So this this infinite series here is bounded above. It is increasing because all the terms are positive. Because every term is positive. So the partial sums are increasing. It's bounded above. Therefore, we know it converges. We have that monotonic sequence. We have, I forgot the name of the theorem actually. we had one for sequences, and there's a similar thing here. We've got it. Well, basically this is a sequence of partial sums. Let's think of it that way. We have a sequence of numbers which look like this: partial S1, S2, the partial sums. This is a sequence of numbers. There we go. It's bounded above, and they are increasing. So we use the monotonic sequence theorem. There it is, monotonic sequence theorem, and that tells us that this series, the sequence of numbers converges, and those are the partial sums. Therefore, the partial sums converge. So therefore, this guy here converges. This converges. So we used our information about the sort of analogous integral to show that the infinite sum converges here. So we use an integral to do that in this case. There's a variety of different ways to get at whether a infinite series converges or not. So now the interesting question is, and we're not, unfortunately, sadly, we're not going to do too much of that in this course, but the interesting question is we now know that the sum of the reciprocals of the squares converges. We know this. And so then the question is, and it converges to what? Something that is less than 2. We even know that, right? We've showed that sum is less than 2. And what number would that be? And this was actually historically an important problem. It's called the Basel problem. And remarkably, I'm just going to tell you the answer here. It's not so easy to figure this out. The answer here is pi squared by 6. I find this just the coolest thing ever. You've got all of the square numbers. You've got the reciprocals of all of the square numbers, and then suddenly out comes that number pi. Doesn't appear anyways at first blush to be at all associated, with a circular function of any sort. And then you've got this number here, 6. 6 is the first perfect number as well. So it's a very exciting result, and it actually took a little bit of time for this to be figured out. And yeah, so have a look at the history of this. It's really interesting. It's the Basel problem, and it's a very cool result. Okay, for our purposes here in Math 152, we would not be expecting to be able to figure this out. We are expecting though to get to here. We should be able to get to saying yes, it converges, and maybe even placing an upper bound on it, or a lower bound as the case may be. But we expect to be able to say something, but we may not be able to get the exact number. That's fine. Okay, so now we're going to take a look at another example. Here is an integral, another improper integral from 1 to infinity of dx over x. And using our knowledge of evaluating improper integrals, we already know that that integral diverges. So let's just recall that in case it has slipped away. That is the limit as t goes to infinity of log t minus log of 1. Log of 1 is 0. Log of t, as t gets large, just continues to grow. This is infinite. The integral diverges. So the area under that blue curve starting at 1, the area under the blue curve starting at 1 is infinite. Okay. Now I'm going to take a look at drawing rectangles that that are a visual representation of this sum. So let us look at the numbers here. What sequence is this? What sequence? Let's try that again. What series is this? This is the harmonic series. And it diverges. We already know this. We had a proof of that last lecture. This is the harmonic series. It diverges. We are going to show here again via another method that it diverges. It really diverges. This is an important point, and you want to have that clear in your head. Okay, so here I'm going to draw visually this sum now. So I'm looking at drawing a rectangle with area 1. I'm going to put that right here. So that is going to be this here. It's height 1, width 1. This is area equal to 1. And then I need a rectangle with area 1/2. So I'm going to have width 1, and the height's going to have to be 1/2. And this place right here is 1/2, right? Because y is 1 over x and x is 2, so y is 1/2. So I've got this area here, then I've got this area here, and then this area here is too many of these black dashes in here. This area here is 1/2, and then you can follow this logic along, and you'll see here that this area here is 1/3. And so when I'm adding these up, I'm adding up 1, 1/2, 1/3, etc. A quarter is going to be here like that. And you can see that the total area under, when I add up all of those shaded black rectangles, is going to be more than the area under the blue line, y equals 1 over x. So we can see here that the sum from n equals 1 to infinity of 1 over n is greater than the integral from 1 to infinity of dx over x. Okay, and this guy here diverges, so that means something bigger diverges. So let me put the conclusion here. The harmonic series diverges. Okay, an important point. Now we've seen two ways of showing that result. Okay, so we've seen in this example and the previous example that we can use an integral to tell us something about the infinite series. So let's just formalize that here when what we're going to call the integral test. Suppose we have a function, continuous positive decreasing on 1 infinity, and let a n be f of n. Right? So we're going to then choose the values at the integers, at the integer of the domain. So we're choosing this n is going to be 1, 2, 3, 4, and then we have the series that is equivalent to that function. And the series converges if and only if the improper integral is convergent. So it basically saying if the integral converges, the series converges. If the integral diverges, the series diverges. Okay, we'll notice carefully that we're going to keep these the same. Okay, so we have one here. Is the series convergent or divergent? So what we do is we consider the analogous integral. So it'll be the integral from 2 to infinity. That's a 2 here, so I've got the 2 here. 2 to infinity of dx over x times log x squared. And we're going to do that via substitution. So we're going to let u equal log x, and then du will be 1 over x dx. And so this integral will become the limit as t goes to infinity of the integral from 2 to t of dx over x log x squared, which is the limit as t goes to infinity. Now I'm going to make the complete substitution. When x is 2, u is log 2. And when x is t, u is log t. and that becomes, and then when I do the substitution, I get 1 over u squared du, which is easy integral to figure out. We've already in fact done this during this lecture. I'm going to get here 1 over u evaluated at log 2 and log t, and then I do the evaluation, and then the final step will be taking the limit. And do the evaluation, I'm going to get minus 1 over log t plus 1 over log 2. I take the limit. This thing is going to go to 0, so this is going to be 1 over log 2. So the integral converges. So then I would say, I'm going to leave myself a little bit of room. I'll put the conclusion in a different color here. So the integral converges. Therefore, the series converges by. In mathematics, a series is the sum of the terms of okay, this is that Siri just decided to kick in with a description of what an infinite series is. It's very strange. Okay, the series converges by the integral test. Okay, so what we do is we evaluate the equivalent integral. If the integral diverges, then the series diverges. If the integral converges, then the series converges. And when you do this, it's nice when you draw a conclusion, you say, okay, I've analyzed the situation. I'm telling you that the series converges, and then you tell the person why. I mean, they can sort of see what you're doing, but especially on a test, it's really obvious when you're marking student work, the person who's extremely clear and their stuff is laid out so that you can see what their thought process is. And when you see it's correct, it takes about 5 seconds to give full marks, right? You're like, oh, I see what they are doing. They articulated what they're doing. It's neat. I can read it. It's done. Sometimes it'll be the correct conclusion, but you have trouble following what they're doing, and then it's more difficult to understand sometimes whether you should give full marks. So just try to be as clear as you can. So it's quite nice to say, consider this integral, evaluate the integral, and even could state here, the integral converges, and then it's like, therefore the series converges by the integral test. Okay, so here's use the integral test to test the p-series for convergence. So this is called a p-series because we have 1 over n to the p. So we had the same thing when we were doing the integrals. We had this. So all I'm going to say here is that there's for recall this integral from 1 to infinity of 1 over x to the p dx, and that was convergent if p was bigger than 1, and it was divergent otherwise, p less than or equal to 1. Okay, so therefore the p-series test here, the sum from n equals 1 to infinity of 1 over n to the p is convergent if p is greater than 1, divergent p less than or equal to 1. Okay, so notice what's happened. If p is equal to 1, we end up with the harmonic series. And that is divergent. It's that line. So I mean, if p is like 1.00001, the series will converge. So it's that very fine, it's that exact first spot where it goes from being convergent to being divergent. So if p is 1, we get the harmonic series, and the harmonic series diverges. All right. What else can we do with this newfound skill? What we can do is we'll be able to use the integral to get an bound on how much, well, to make an estimate of the sum. We might not, like we saw in our first example, we might not be able to figure out what the exact value of the sum is, but we'll be able to use integrals to get a bound on it. So that's what we're going to be doing here. So when we make if we have an infinite series here and it's convergent, the nth remainder is, we're going to define this way here. I'm just like, this should be then. This was causing me grief. Okay, so the what we call the nth remainder is the difference between this is the actual sum, okay, the exact sum, and then that is the nth partial sum. So what we're doing is, I mean, our nth partial sum, we're going to add up the first n terms, and then of course there's some exact value, which would be adding up all the infinity terms, all infinite of the terms, and then the remainder is the nth remainder is the difference between those. I mean, they're the ones that we didn't add into the nth partial sum. Okay, so here we have a function on an integer, which is this k is an integer, and f of k is going to be ak. F is continuous positive decreasing function, and when we have a convergent series, and then we have the remainder, we can bound that remainder. So this is the remainder here. We can bound that remainder by this integral below and this integral above. What is the difference between these two integrals? Let's make sure that we know. The only difference is this right here. So how much ever we're going to be out, we can estimate our sum, and how much we're going to be out is going to be bounded below by the integral from n plus 1 to infinity, and it's going to be bounded above by the integral from n to infinity. And there's a couple of diagrams to show you that here. So we've got y equals f of x, and you can see that the integral from n to infinity, that is right here. Right here. Let me just do it here like this in red. What I've shaded there in red is the integral from n to infinity of f of x dx. And you can see that, which is this right here, is bigger than the terms that we didn't include, an plus 1, an plus 2, like that. Okay, so that is an upper bound. And then there's another diagram here showing that if I take the integral, so now this area here in red on this diagram is the integral from n plus 1 to infinity of f of x dx. And you can see that the remainder, the terms I didn't include, which are these guys here, the sum of all these, that's my remainder term. You can see that it is more than that integral. That is why those two integrals are providing a upper and a lower bound. Okay, we'll do an example of this and see how this works. Okay, we've already showed that this thing converges. I'm just going to actually not tell you how I got this number, but I'm just going to put this here so we can see as we go what's happening. So this is approximately 2.10974. Okay, so we know it converges. I mean, in some ways we know it converges. So if you want to know approximately what the sum is, you have a computer and you just add up gazillion terms. You can add up 10,000, 100,000 terms, and you'll get an estimate, because you've showed it converges, so it's totally reasonable to add it up. And then once you stop, you're going to say, okay, I added up 10,000 terms. I got this number. That's approximately what it is. And then I'm now going to try to get a bound on how much I'm out by. I'm going to try to bound that error. Okay, so I'm going to see here how many terms would we need to add. So how many terms would we had to tell our computer to find the value of this sum accurate to within 0.01. So how large does n have to be for the remainder to satisfy the inequality? The remainder is less than 0.01. Okay, so what we want is this remainder to be less than 0. So that means whatever number, we're going to add up a whole bunch of terms. We're going to give you some number for the sum. We don't know exactly what it is, but we're going to guarantee you that we're within 0.01. And I'm asking myself, how many to what number do I have to go here on the top in order to make that happen? Okay, so the remainder is bounded above by the integral from n to infinity of f of x dx, and I want that to be less than 0.01. Okay, so then I take the integral from n to infinity of 1 over x log x squared dx, which we already did from before, so I'm going to just write that down. This is going to be 1 over log n. This is from earlier. If you're not sure about doing the improper integrals or the substitution, actually now is a good time to say, oh, I just saw that. Maybe I'll stop, do this integral again, and make sure I come out with that result. Okay, so now I've evaluated that. I know that this integral, I'll just write it like this. This integral which is equal to this, is going to need to be less than 0.01. Okay, that's right here. So that means that the 1 over log n, well, I'm going to rewrite this. 1 over log has to be less than 0.01, and log n, that means is going to have to be greater than 100, and that means that n is going to have to be greater than e to the 100. Holy, that is huge, huge. Okay, so this infinite series converges very slowly. This series converges very slowly. So we have computers, very fast computers at this time in our history, so we can actually do lots and lots and lots of computations. But even lots and lots of computations, if we had some really pressing need to accurately know what this sum was, we would either have to figure it out exactly, or we would have to say, we got to do something other than adding up e to the 100 terms just to get to within 1% of the correct answer. That would be horribly inefficient. So there's actually quite a bit of work done in some topic which would say typically be in, say, numerical analysis, where people are looking at methods of speeding up convergence and doing things so that you can get to a approximate answer with a guaranteed error bound more quickly. So this would be the brute force method of doing it, and it's not very efficient. So let's just take a look what would happen. So I gave you an indication here of the what was that, 1, 2, 3, 4, 5 decimal place approximation there. I'm going to just show you what happens if I was to go in a computer and go from 2 to 100 of this thing here. I would get approximately this number. I get this number here, 1.8928 approximately. Okay, and then I would go again. I would say, okay, so I go from 2 to 1,000. This is also not hard for a computer to do. And I would get 1.96 96, what did I get? 4988, 4988. Okay, I could then go again from 2 to 10,000, and I would get n log n squared, and I get 2.0011. So you can see I am approaching that number I gave you at the top. Well, we don't actually even know the exact number here, but I'm at 10,000 terms, and I've only got this thing here, right? I haven't even got to within 10%. So that's pretty lousy in that it converges very, very slowly. Similarly here, we know that the error, we've made this calculation, we know that the error is bounded above by this. So we know here we do know the error. The error in this calculation is bounded above, so the error is less than or equal to 1 over the log of 100, like that. Okay, here we know that the error is less than or equal to 1 over the log of 1000. Okay, so you can compute what those numbers are, and you have a bound on the error. And the reason why it is converging so slowly is that this error bound, the logarithmic function, grows so very slowly, right? It sort of starts out fast. Let's just draw a quick picture of the log function to remind ourselves. This is coming up here like this. And so this is a very here the rate of change is very low. It grows very slowly. I mean, it obviously grows very quickly down here, but once the n gets big, and we're talking about numbers here already at 1,000 or 10,000, so the growth of the log function is very slow. Okay, so just to recap what we talked about here, we can use the equivalent integral in order to get an estimate for a sum. And we can provide a lower and upper bound for the sum using an integral. And we can sort of, in some sense, by increasing the number of terms that we're using to compute the sum, we can get closer and closer to the actual number, and then we can provide a bound on the error, so that we can say with some assurance, oh, the number is this, to within 0.05% or that sort of thing. That may well be good enough for the application that we are using. So this is called the integral test. You can use it for convergence and for bounding the error on an estimate of your sum. Okay, that is all for the integral test. We will be back shortly with another test on how to find whether a series converge or not. Thank you.